Hello everyone, this video covers section 3.5. The title is cubic splines. Alright, the idea is pretty simple. Let's say that we have a function, okay, so that we're trying to approximate the function at endpoints, okay? So this will be a, which we also want to call x0, and this will be xn, which is also b. And therefore we're going to divide this into n intervals x1, x0 to x1, x1 to x2, and so forth, all the way to xn minus 1 to xn. Okay, and the idea is that at each interval we're going to find a cubic polynomial. Okay? Now in theory, based on the topic from last section, from 3.4, you can technically find Hermite polynomials. Actually, let me be more specific. It will be easy to find h3 in each interval. So for each interval, so it will be easy, except for one thing. The Hermite polynomials require that you know the derivative of the Lagrange polynomials, which you may not know, or most of the time are not available. So therefore this may not be very practical. So instead we're gonna go with cubic splines interpolants. So the idea is the same. We divide the interval into n small intervals, and in each of them we're going to find a cubic polynomial. So this will be one polynomial, another cubic polynomial, and so forth. So when you add all of them, it will give you S. So S is going to be called the cubic spline interpolant. So S is just going to be a sum or a pretty much a piecewise continuous that will have n different cubic polynomials, and when you add all of them, you still have a cubic polynomial. Okay? So that's the idea. The idea is you find a cubic polynomial here, a cubic polynomial here, here, and so forth, and then you create a piecewise function, which is what we're going to call S of x, and that will be the cubic spline interpolant S. Now in order to get S, it has a bunch of conditions that you have to satisfy. So here we have all of them. The first one, or part A, I already mentioned it. So S of x will be a cubic polynomial, and each Sj on the interval xj to xj plus 1 will be also a cubic polynomial. Then the value of the j polynomial has to match the value of the function at the endpoint. So at this point, they had to match with the function. Also, the previous polynomial has to match with the next polynomial at that point. In other words, that will make the function continuous. As you can see, this point is the same for this polynomial, but it's also for S1. So at this point, S0 and S1 are the same, just like here, S1 and S2 are the same, and so forth. So that's what condition C means. Then condition D says that the derivative, not only they had to match at the point, but they also had to match in the derivatives, and they also had to match at the second derivatives. And then for condition F, you have two choices. If the second derivative is equals to 0, remember what does the second derivative equals to 0 means from calculus, so just think about that. This one is going to be called a natural or free boundary spline. Now if we use the first derivative instead at the endpoints, so that means this and this s prime of j of x n is equals to the n derivative of xn, then this one is called a clamp boundary. And depending on whether we're using this boundary or this one, the process is slightly different. Alright, so let's try an example and see how this works. Alright, the question says this: construct a natural cubic spline that passes through the given points. Remember that natural means the second derivative of j evaluated, at x0 has to be equals to the second derivative evaluated at the other endpoint, and not only that, it has to be equals to 0. Here we have the following points. You have x0, x1, x2, x0 is equals to 1, x1 is equals to 2, and x2 is equals to 3. And then f of 1 is 2, f of 2 is 3, and f of 3 is 5. Remember that this is f of 3, and this is f of 1. Okay. Remember that in general, you have a cubic polynomial, looks like this. Okay. A cubic polynomial has the following form. This should be no surprising, but make sure you see this. So Sj of x is going to be equals to aj plus bj x minus xj plus cjx minus xj squared plus dj x minus xj cube. So this is the general form of a cubic polynomial. So all you have to do is figure out the constants and you're good. Here we need only two. We need s of 0 of x, which would be a0 plus b0x minus x0, which is 1, plus c0x minus 1 squared, and then this 0 times x minus 1 cubed. So we need this one. And we also need s1, which you just replace the 0 with the 1, but now this will be x minus 2 instead of x minus 1. Okay, so in essence, you have 4 variables for this one that you need to figure out, and this one also 4. So in general, it's going to be 4 n variables that you need to figure out. Here n is equals to 2, so therefore we need to find a variables. So you need to find a variables. Alright, so this is part A. Now for part B, this is what we have. Part B is telling us the s0 of x0 has to be equals to f of x0. So that implies that s01 is equals to f of 1. So that means that a0 plus b0 times 0 plus c0 times 0 and d0 times 0, that this has to equals to 2. How do we get the 0 here? Well, if you put 1 in here, that will give you 0, 0, 0, so 4. So therefore from here, this implies that A0 is equals to 2. Okay? And let's call this equation number 1. Alright, then S0 of x1, this should be equals to f of x1. So that implies that f of, this implies that S0 of 2 should equals to f of 2. So this means now that A0 plus B0 plus Z0, and this 0 has to equals to 3. Why? Because f of 2 is 3, and if we plug in 2 in here, 2 minus 1 is 1, 2 minus 1 is 1, and we end up with this. So therefore from here, we end up with the following equation, B0 plus C0 plus D0 is equals to 1. Remember that A0 is equals to 2. So if you move this to the side, you will get the 1. And this would be equation number 2. Right now for part C, remember part C is going to make sure that the endpoints of the different polynomials, they match. So therefore for this one, we need S1 of x1 has to be equals to f of x1, or S1 of 2 should equals to f of 2. Again, this one is easy to solve, so this will be A1 plus 0 plus 0, and this should equals to 3. So from here we got that A1 is equals to 3. And this is now going to be equation number 3. Now in a similar way, we need to figure out what is S1 of x2. And this has to equals to f of x2. So from here we have that S1 of 3 has to equals to f of 3, or the A1 plus B1 plus C1 plus D1 has to equals to 5. And from here we get equation number 4, which will be this B1 plus C1 plus D1 has to equals to 2. Okay, basic algebra. And this is equation 4. Now in part D, we need the derivatives. Remember that S0 of x is equals to this A0 plus B0 x minus 1 plus this 0 x minus 1 squared, and so forth. So therefore the derivative is going to be equals to B0 plus 2C0x minus 1 plus 3D x minus 1 squared. Now, since we're going to need the second derivative eventually, that means the S double prime is going to be equals to 2C0 plus 6D0 times x minus 1. Now if we do the exact same thing for S1, so remember x1 was equals to A1, B1, and so forth. Okay, so if we take the derivative, this one should be Q. We get the following. The S1 prime will now be equals to B1 plus 2C1 x minus 2, and then 3D1 x minus 2 squared. And the second derivative is going to be 2C1 plus 6d1 x minus 2. Okay, remember to satisfy part D, this means the s1 prime of x1 has to equals to s0 prime of x1. Or in other words, that means that s1 prime of 2 has to equals to s0 of 2. So this means the b1 plus 0 plus 0 has to equals to b0 plus 2 c0 plus 3 d0, and from here we get equation number 5, which will be this b0 plus 2 c0 plus 3 d0 equals to b1, and this is equation number 5. Alright, so now part E says the following: that s1 double prime of x1 has to equals to s0 double prime of x1, which means s1 double prime of 2 has to equals to s0 double prime of 2. Or in other words, this is equals to 2c1 equals to 20 plus 6d0. And from here we found equation number 6, which will be this: c1 is equals to c0 plus 3d0. So this is equation number 6. All right, now part F. Remember that we're using that we need to find the natural cubic spline, and natural means the second derivative at the first endpoint should be equals to the second derivative at the second endpoint, and it has to equals to 0. So this will make life a lot easier. Why? Because this means the following. This means the second derivative of 1, evaluated at 1, has to be equals to 0. So from here we have 0 is equals to 2z0 plus 6d0 times 1 minus 1, and you automatically get that c0 is equals to 0. Then we also have the second derivative evaluated at x2 should equals to s double prime evaluated at 3, and that means 0 is equals to 2c1 plus 6d1, and from here we get 0 is equals to c1 plus 3d1, and this is equation A, and this will be equation 7. Here remember that this means this s0 double prime of x0. Now to solve for this variable, it's going to be a little messy since you have 8 different variables you had to figure out, because remember the number of variables is equals to 4 for n. Here we're only doing 2 intervals, and most likely that's what you will have to do for the test and the quiz. If you have more than that, then to solve this by hand it will take a long time. Even with 2, you see right now there's a little challenging. You just have to play with the equations and eliminate variables, just like you did in pre-calculus, but it could get more messy. So let's see what we have so far. So far we have equation 2, which was the following: b0 plus d0 is equals to 1. Equation 6 was c1 is equals to 3d0. Equation 5 was b1 equals to b0 plus 3d0. and then equation A was 0 is equals to C1 plus 3D1. So notice how this one you can simplify to D1 is equals to minus D0. So therefore equation 6 and equation A, if you combine it, it will give you this equation, that D1 is equals to minus D0. Now you don't have to, but you could technically call this equation 9 if you want to. Now remember that equation number 4, okay, so equation 4 was the following. It was B1 plus C1 plus D1 is equals to 2. However, if D1 is equals to negative D0, then from here we'll have now that B1 is equals to 2 minus 2D0 by substituting this 1 by D0, and also remember that C1 is equals to minus 3D1. And again, it's not required, but you could technically say that this is now equation number 10. Now remember that equation 5, which is right here, we have that B1 is equals to B0 plus 3D0. Or we have B0 plus 3D0 is equals to B1, which you can simplify this to B0 plus 3D0 equals to 2 minus 2D0. And you substitute this in here instead of B1. And then this simplifies to B0 plus 5D0 is equals to 2. And technically, you can say this is equation 11, but it's technically just equation 5. Therefore, if you combine 2 and 5, we will get the following. 2, remember, was B0 plus D0 is equals to 1, and 5 is now B0 plus 5 D0 is equals to 2. Now this is a 2 by 2 system from elementary algebra, which you can solve pretty easily. You should check this. Stop the video and check this. D0 is equals to 1, 4. D1 is equals to negative 1, 4. So therefore this implies that B0 is equals to 3/4. Why? Because B0 is negative 3 times this one. Also notice from here that 0 is equals to C1 plus 3D1. This gives you that D1 is equals to minus D0, but this also implies that C1 is equals to minus 3D1. So from here that means that C1 is equals to 3/4, and therefore B1 is also equals to 3/2 once you solve. So you have C1, B1, B0, D1, D0. And remember from equation 7 that C0 was equals to 0. So this was from equation number 7. Alright, so therefore the solution, the cubic spline will be this. It will be 2 plus 3/4 x minus 1 plus 1/4 x minus 1 cube, when x is between 1 and 2. And then this one will be 3 plus 3/2 x minus 2 plus 3/4 x minus 2 square minus 1/4 x minus 2 cube, when x is between 2 and 3. And that's it. Again, this is not hard, just pretty messy and you have to keep track of all the equations. Like I mentioned a few minutes ago, in the book, it has two algorithms to code in MATLAB, one for the natural splines, which is what we're going to focus on, and the other one for the clamp boundaries. And again, on the quiz and the test, you will only have to find up to two interpolating polynomials. So therefore, n will be 2.